Having said that, you might still think that the relative difference between these two models is, between the PFR and the average model is not all that large, and qualitatively, at least the dynamics seem to be similar to what the PFR model predicts. So in that sense, the method of averaging, or the full power of the method of averaging, is not revealed in this relatively simple example. Nevertheless, we took this simple example because it allowed us to illustrate the method of averaging. But to show you that the averaging method can really be powerful and predict things that qualitatively cannot be captured by like simple heuristic plug flow models, let me end this lecture by quickly showing you just a demonstration of the application of this method to a more complex problem. So we shan't look at any derivations, I'll just show you some results. So for the more complex and more realistic real world application, let's look at two-phase solvent extraction in microchannels. So this is something that I worked on during my PhD days with Pushpamanam in IIT Madras, and the paper is given below here. So essentially in this problem you have two liquid phases flowing side by side inside a microchannel. If you look at it through the microscope, you can see something that looks like this. So you have two phases, one of which has a solute, and the objective is that you make the solute rich phase come in contact with some extractant phase, and the solute gets transferred to the other phase. In some case it undergoes also a reaction in the other phase. And this is a basic operation in separation processes, in various other applications, in bioassays, etc. So a model for this system would involve, in this case I'm looking at flow between flat plates for simplicity, but you'll have flow in between, you'll have two phases flowing. We assume the interface to be flat, as it often is in such microchannels because surface tension keeps it flat. And basically you have advection and diffusion. So you have transverse diffusion, you have axial advection in the x direction. So this is the advection diffusion equation now in phase 1. And similarly you have another equation in phase 2, but we also allow for the possibility of having a reaction in phase 2. So you see the Peclet times Darmkohler term with the reaction rate in the second phase. And P is the same axial Peclet number, so it's the same scaling as we did in our derivation here. So proceeding, you see that we have the no flux boundary conditions at the wall, and at the interface we have a kind of equilibrium boundary condition relating the two concentrations on either side of the interface, a thermodynamic equilibrium boundary condition, and a conservation of flux. So these are standard boundary conditions. The velocity field is also kind of a Poiseuille flow, but extended to two phases, which is trivial to obtain. So it's a known velocity field. Now, if you do an equivalent of the plug flow model for this problem, what you would do is you would assume that the concentration, there's perfect radial diffusion, right? So the concentration is assumed to have no variation in the y direction, right? There's perfect transverse mixing, and so therefore C1 is uniform in phase 1, C2 is uniform in phase 2, and C1 and C2 must be related by this equilibrium thermodynamic condition. So a simple heuristic model would say that there is a cup mixing average C1 equal to K times the average C2, and that average is basically the same throughout the channel. And so you substitute that into a kind of advection equation, but which is integrated over the whole channel. So you get the following. So the transport by both phases are accounted for in this advection term, and you have reaction only in the second phase. Again, the reaction rate is evaluated at the average concentration, which we know itself has some errors. In any case, this is a heuristic model which assumes perfect transverse mixing, and it's a sort of thing that is an equivalent of a plug flow model. But then you can also do systematic averaging, just as we did in this lecture, but now we have it for two phases. So therefore you have these two ODEs in X. At the same time, other than just a reaction, you also have loss of material to flux through the interface. That flux is denoted by J. So that flux is of course dependent on the X direction, right? The flux or the rate of transport is higher near the inlet and it decreases near the outlet as the phases approach equilibrium. So you see the averaged equation for phase 1 is similar to what we had obtained, except that instead of a reaction you have this flux term, and that flux term comes into the expression for the difference in the cup mixing average denoted by C hat and the cross section average denoted by C bar, and the advection term has the cup mixing average, and you have this flux J. J, the expression for J comes later. Similarly for phase 2 you have advection involving the cup mixing average in phase 2 balanced by the flux coming into phase 2 and the reaction rate in phase 2. You have a difference between the cup mixing average and the cross section average here as well. And importantly, the flux terms, which as yet are unknown, are given in terms of a difference in the cross section average. And the reaction rates, of course, are all evaluated at the cross section average. So you can see that to solve the model, you do need a relationship between the cup mixing and cross section average, because the flux is given in terms of the cross section average. In any case, this is a kind of two-phase extension with interface mass transfer of the average model we derived for just single phase flow. Now let me show you some results. So let's look at the case of only extraction or only mass transfer without a reaction. So you set Darmkohler to be 0 in these models. So all you have is the flux J, which accounts for transport of C1 into C2, and the expression for J depends on the difference in the cross section average. Right? This is basically, you can interpret it as a thermodynamic driving force in terms of the cross section average concentration, and this denominator, 1 over the denominator, is like a mass transfer coefficient. And importantly, usually we derive mass transfer coefficients experimentally, right? We write a flux J equal to concentration gradient driving force C1 minus KC2 times a mass transfer coefficient. Here I have the mass transfer coefficient analytically obtained by the averaging method, and these gamma 1, gamma 2s are known constants that depend on the nature of the flow field. In my case, it's some kind of parabolic pressure driven flow, but you could do the same thing for electroosmotic flow and obtain different results. That of course has not been done. So now let's compare the results. You have three different curves here. The solid, the blue is phase 1, the red is phase 2. The continuous lines are the exact solution of the full partial differential equations. You see that as expected, the solute enters in phase 1, and as you go down the length of the channel, it gets transferred into phase 2. So the concentration in phase 2 increases. Now importantly, this short dotted line is the heuristic model or the equivalent of a plug flow model. You see that it doesn't predict any variation. Instead, it directly predicts the equilibrium concentrations, right? Because you're already assuming perfect transverse mixing. So a plug flow model which doesn't account for concentration variations cannot predict any rate of mass transfer. It could have predicted some variation if there was a reaction, but in the absence of the reaction, it's completely useless, the plug flow model. But you see, the average model gives you excellent predictions of how solvent extraction proceeds. Right? And remember, the average model here is basically varying only in the x direction. It only requires discretization in one direction. The PD, of course, is in x and y. So the computational savings of this average model shown by the large dashed line is quite significant compared to the solid lines of the PDE model. Yet its predictions are almost as accurate. So this really shows you the dramatic power of averaging, especially because qualitatively it gives you superior predictions to the, basically the plug flow model in this case is completely useless. It just tells you what will be the equilibrium concentrations, which you could have, that you already know. You don't even need a model for that. Okay, another thing, so ignore this TAE model, that's just a name I gave it, but the average model lets you, like I said, without the reaction, the mass transfer can be written as a driving force times a coefficient. So in non-dimensional terms, this is my Sherwood number. Yes, so I obtain a Sherwood number for this specific flow analytically without doing experiments. And because I have it analytically from my average model, I can look at how the Sherwood number or the non-dimensional mass transfer coefficient varies with various parameters. So here I am plotting it relative to h, which h is the relative height of the two phases or the hold up. Right? So it's the relative thickness of the two phases in flow. So I can vary this by varying the relative flow rates of the two phases. And you see, as I vary h, the mass transfer coefficient attains an optimum at some point. These different curves are for different values of the relative viscosities. So I can control both the fluid viscosities, maybe by adding additives, and by changing the flow rate I can control H, and therefore I can optimize my mass transfer. And for this I don't need to solve repeatedly PDEs and use some optimization procedure. I can just look at it here because I have the analytical result. So again, you see the power of the averaging method, and the physics it tells us from this calculation is quite useful also. It says that the mass transfer coefficient is greatest when you have a more viscous fluid occupying a larger holdup. Okay, and the last interesting thing is now the model, in the absence of a reaction with just mass transfer, can be solved analytically, and these are the analytical solutions. And from the solutions I can identify this parameter lambda, which is locked inside this exponential decay of the concentration of C1 and exponential increase of the concentration in C2. In either case, lambda denotes a characteristic length. It tells me how quickly I am going to reach equilibrium along the length of the reactor. So the greater lambda, the faster I reach equilibrium in terms of residence time inside the reactor. At the same time, I can look at the limit of infinitely large reactor and look at the final extent of extraction at equilibrium. So assuming I have an infinitely long reactor, I can give infinite residence time. What is the maximum extraction? That I can also calculate analytically. That's given by this extraction ratio at equilibrium. And the nice thing is I can plot both of them versus the different holdups, right? So if I adjust the flow rates and I change H, which is plotted along the horizontal axis, I will get different speeds of extraction given by lambda and different maximum extents of reaction at equilibrium given by this ER. And the truly interesting dramatic thing to note here is that I can get a maximum speed given by a minimum in lambda for some H, let's say 0.4 here. But that H, that holdup is exactly where I get the maximum, I get a minimum speed. So lambda is proportional to the speed of extraction. I get a minimum speed at some H, but that speed is exactly the speed where I get the maximum possible extraction at equilibrium. So this indicates a trade-off between extent of extraction and the speed of extraction. And this is quite typical of these mass transport and in general finite rate problems, right? So if you want to maximize the extent of the process at equilibrium, you have to go very slowly. If you try to go quickly, you have loss of efficiency. And this thing comes out analytically and quite beautifully here from the averaging procedure, something you may not have realized if you just did numerical calculations of the PDE model. Okay, so with that, I will end this lecture with this demonstration. I would like to point out, of course, so if you want to know more about this application, it's given in this paper below. But more importantly, the derivation I did in this course, the reference will be provided along with this link. If you are viewing this lecture on YouTube, you can look at the description. Or if not, I'll just give it to you now. It's a paper by Chakraborty and Balakotaya in Chemical Engineering Science, volume 7, published in 2002. Volume 57, published in the year 2002, and I'll give the reference in the link. So it's really quite a nice paper. It goes into the details of the calculation for a single phase tubular reactor. And then this paper mentioned below on this slide shows you another interesting application for two-phase reactive extraction. So I think with that, that brings us to the end of our consideration of the averaging methods. I hope it shows you some of the powers of, again, a more generally asymptotic procedure, right? So that's what our course has focused on. Firstly, looking at full models, scaling them, and from the scaling, understanding the balance of the physics of our problem, and then making certain simplifications almost immediately. And then we looked at perturbation methods as a way to improve those simplifications in a systematic way, right? By doing perturbation calculations or asymptotic calculations in small parameters that we obtained after scaling. And finally, this averaging is another variant of this asymptotic method, applied specifically to problems with rapid diffusion in directions which have no flux boundaries. That's the application we've seen here in this course. And you've seen how it can lead you to models that give you a lot of insight and also have strong predictive power with limited computational cost. So I thank you for your attention, and that brings us to the conclusion of our consideration of these averaging methods. Thank you.